Before we get into another example of indefinite integration, I think it's worth taking a bit of a step back at this stage in the course and discuss, well, in general, if we're just given an integral with no indication of what method to apply, how would we go about figuring that out? Because that really is one of the central challenges of integration, and much more so than we had for differentiation. Because with derivatives, we knew if it was a function involving, say, a quotient that we wanted to differentiate, we were going to use the quotient rule. While yes, we had some ways around that, like logarithmic differentiation, for instance, generally speaking, quotients meant the quotient rule, products meant the product rule, composite functions meant the chain rule, and so on. And there wasn't much ambiguity in that. There is plenty of ambiguity when it comes to integration. Two very similar integrals could be integrated through very different methods, and of course the same integral could have more than one integration technique applicable to it. Unfortunately, there is no hard and fast set of rules for how you decide what method to use to evaluate a given integral. It'd be lovely if they existed, but they just don't. There's just too much variation in terms of the functions that we may be asked to integrate. But we can generate a general strategy, a set of guidelines, which, while not airtight, will certainly help, especially now that we've got a few methods under our belts. So we can call this, let's say, guidelines for indefinite integration. And because we are going to add some more techniques later on in the course when we get to Unit 3, let me be clear that this is a work in progress. And so how would we approach it if we just had some general integral of f of x? Where f of x could be absolutely anything. Well, we'll consider the following. Deciding how to evaluate the integral. And the first thing we should always think about is this a simple integral? We never want to apply a more sophisticated method, a more complicated method, if we don't need to. Because it's, in the best case scenario, going to take more time to set that up, and in the worst case scenario, may lead to more opportunities for mistakes, arithmetic mistakes, algebraic mistakes, differentiating when you're supposed to be integrating, all the easy things that you can do inadvertently when you're doing, well, really any mathematical problem, certainly an integral. So first thing we should always ask ourselves is this an elementary integral? So in other words, this would include any of our common integrals, the list of, 14 or so that we developed right back at the start of the semester. It would also now include our inverse trigonometric integrals from section 1.3. And it would include any combination of them for which the basic properties apply. So sums, differences, constant multiples. But of course not products, not quotients, not composition in general. The other situation that we can treat as an elementary integral would be our case of linear composition, because we do at least have a pattern there that we were able to prove then using u substitution, so we know how that type of composition works But remember, we can't generalize that, unfortunately, to other types of composition. So it includes our common integrals, our inverse trigonometric integrals, any combination of them for which the basic properties apply, as well as instances of linear composition. If the integral is not an elementary integral, the next thing we should look for is to see whether we can rewrite it as an elementary integral. Remember when I was first outlining the general strategy for integrals back in section 1.1, step 1 was rewrite the integral if it was appropriate to do so. And that never changes. If we can rewrite the integral, which removes the need to look at more sophisticated techniques, that is often a good way to do it. So can it be rewritten in terms of elementary integrals? Again, as a sum, as a difference, or as a constant multiple. And so here, how we might rewrite it, we could do this algebraically. Multiplying things together, expanding out powers, lots of algebraic possibilities. We could use trigonometric identities. We could use long division. We've seen that that's very useful for improper rational functions in particular. We might have to complete the square, especially as we've seen with our inverse trigonometric type integrals. And there may well be other ways to take an integrand and rewrite it, but they should be reasonably obvious ways. If we really got to jump through hoops in order to try to get something into an elementary type form, that's probably not the way to go about it, or at least that's something you'd come back to and think about if you've exhausted any other possibilities. If those don't seem to be good options, that's when we turn to our more sophisticated techniques. And U substitution will usually be the first such technique that you'd think about because it has the widest applicability. U substitution can be applied to the largest array of different functions of any of the other techniques that we'll see in Math 1001. So is U substitution appropriate? And often then we're going to be looking for composite functions, and we're going to try letting U be the inside function, but not always. And very often what we're looking for is an expression whose derivative, maybe without a constant multiple, is also present in the integral. But even that isn't a hard and fast rule, and we'll see that with the example that we're about to do. So I'm going to leave that question just at that, because the appropriateness of U substitution, there are lots of ways it could turn out to be appropriate. But if so, that is almost certainly the best way to go if we've already eliminated elementary approaches. Then I would turn to integration by parts. Integration by parts also works in a pretty varied number of situations, but not as much as U substitution. Again, we're often looking for it from products, the same way U substitution is often going to happen in the case of a composite function, but again, not always. And we've seen how we can sometimes use integration by parts when we don't technically have a product, because we could let W be the integrand and let dV simply be the differential. We've seen how that works. So we'll try using elementary techniques. We'll try rewriting it in terms of elementary techniques if that seems reasonable. Then we think about U substitution. Then we think about integration by parts. And then finally, we would think about, well, maybe we can combine these things. And as we've already talked about today, we've seen how sometimes we can combine U substitution and integration by parts in either order. But we never start off by looking for that. We'd go to that if we basically kind of eliminated all the other options. So possibility 5, we'd ask the question, does the integral require a combination of techniques? And you work your way through those 5 questions. That will typically guide you to the right method or methods, because as I said, there may be more than one that could work for a single integral. And in Unit 3, we're going to come back and we're going to pick up and we're going to stick some new options right here around step number 4. But that's several weeks down the road yet. We won't worry about that here today. So let's think about exactly these guidelines in the context of the next example. And here this is going to seem simple. This is going to seem like a very nice little integral. It's going to be the integral of the sine of the square root of x plus 2. So let's go through these 5 steps if we get that far. So step 1, is this an elementary integral? No. Might look like it is. So you might think, well, isn't it just a sine function? Don't we know that the integral of sine is negative cosine? But it's a composite function. We've got that square root inside the sine function. And there's no simple way, based on the results we've generated so far, to deal with that square root. Because the only type of composition for which we have a nice global result is linear composition, and this is not. The square root means this is not a linear function. So if that square root wasn't there, if we were just integrating sine of x plus 2 on its own, then absolutely that pattern for linear composition would apply, but it doesn't work with the square root. And you'd know that, because if you did try to apply something along the lines of that linear composition formula, got your result, and then tried differentiating to check your answer, you will not get back the sine of root x plus 2. So no, not an elementary integral. Can it be rewritten in terms of elementary integrals? No, that doesn't seem feasible here. We don't have trigonometric identities, for example, for the sine of a square root or the sine of any power in general. So no, doesn't seem to be any way to rewrite the integrand in this case. Could we do a U substitution? Well, it's a composite function, which suggests maybe U substitution is going to be helpful. But the problem is that the only thing that we could apparently let U equal would be that square root of x plus 2. And when we differentiate it, we get a multiple of, well, if you differentiate root x on its own, you get x to the negative a half, so in other words, 1 over root x. So here we get a multiple of 1 over root x plus 2, and there isn't a 1 over root x plus 2 in our integral to get paired with that. So it looks like we're missing the stuff that we would need for a U substitution. So, okay, no, it doesn't look like U substitution is appropriate. What about integration by parts? Well, the only way we could set that up would be to let W be this whole function, sine of root x plus 2, and that's certainly going to get messier when we differentiate it. So we differentiate sine of root x plus 2, we'd have to use the chain rule. We get the cosine of root x plus 2 times the derivative of root x plus 2 again. So again, we'd have a multiple of 1 over root x plus 2 in there. So that doesn't seem to work either. And then a combination, well, maybe, but if neither U substitution nor integration by parts on their own seem to work, How could we somehow combine them? Except that, hang on now, when we talked about both of these options, both u substitution and integration by parts, we pointed out that we're going to wind up with a 1 over root x plus 2 either way. And that seems like a problem, except while it is true to say that there is no 1 over root x plus 2 here in our integral, root x plus 2 is the very thing that under a u substitution we would be setting equal to u. So maybe there's something we can do with that. Maybe we could start off trying a substitution along those lines, and maybe it'll work on its own, or maybe then it will lead to a combination of techniques. It's at least worth exploring. And that's the thing with integration. Sometimes you've got to give yourself the freedom to try something, and if it doesn't work, so be it. That's just how things work out sometimes. But especially if you keep your eyes open for opportunities to perform some clever mathematics, sometimes it could lead you in the right direction. So let's give that a go. Let's try letting u equal the square root of x plus 2. And as I said, to get du, we'd apply the chain rule. Remember, of course, this is really a power of a half. We get a half times x plus 2 to the power of negative a half times the derivative of x plus 2, which of course is just 1, times dx. Or in other words, I can write that as 1 over 2 times the square root of x plus 2. And again, apparently that's a problem, because we don't have a 1 over root x plus 2. The half here, that being missing doesn't bother us, because that's just a constant. We know how to deal with that. But that seems problematic, except that's our u. So if du is 1 over 2 root x plus 2 dx, that means it's also equal to 1 over 2 times u dx. And remember, our whole goal here is to find an expression for the differential dx in terms of u. So if du is 1 over 2u times dx, then that means that dx, if we multiply this across, is 2u du. So will that give us dx just in terms of u? It certainly seems to. Let's continue this in the next video.